We stand at a remarkable moment in history. Artificial intelligence is reshaping our world. It promises to cure diseases. It promises to solve climate change. It promises to unlock new forms of creativity. This incredible growth feels limitless, a digital frontier stretching out before us. But this expansion comes with a hidden cost, a physical reality that we often ignore. For every seamless answer from a chatbot, for every stunning image generated from a prompt, there is a massive, humming, and very real machine behind the curtain. The engine of modern AI is not just code. It is a sprawling network of data centers, vast industrial buildings that demand immense resources from our planet. These data centers are the physical embodiment of the cloud. They are warehouses, not with boxes, but with tens of thousands of servers. Servers stacked in racks from floor to ceiling. Each server is a powerful computer, working in unison to train and run large AI models. The single greatest resource demand for artificial intelligence is electricity. These systems are incredibly power-hungry. Training a single large AI model can consume a staggering amount of energy, feeding the model trillions of data points over weeks, months. It requires thousands of specialized computer chips running at full tilt 24 hours a day. One training run can use as much electricity as hundreds of homes for a year. This is not a one-time cost. Once trained, models must be run or deployed to answer questions and generate content. Every user interaction draws significant power. By 2027, estimates suggest the AI sector could use as much electricity annually as a country the size of the Netherlands. Netherlands, visual emphasis. Sweden, visual emphasis. Asking a generative AI to write a poem, summarize a document, kicks off heavy computations in distant data centers. Those computations use far more energy than a traditional internet search. A simple Google search is like flipping a light switch. An AI query is like turning on every appliance in your kitchen at once. This demand is straining electrical grids worldwide. Utility companies warn they may not keep up with demand from new data centers. In Northern Virginia, Data Center Alley, infrastructure is being pushed to its limits. Building new power plants, upgrading grid infrastructure takes years and carries environmental and financial costs. The race to power AI competes for electricity, potentially driving up costs for residential customers, other industries. We're building a new digital layer that needs a parallel expansion of centuries-old energy systems. The problem worsens depending on where the electricity comes from. Some tech companies invest heavily in renewable energy, but a significant share still comes from burning coal, natural gas. AI's growing energy footprint contributes directly to carbon emissions and climate change. The promise of AI solving environmental problems is undermined if it becomes part of the problem. We cannot separate AI's digital output from the carbon output required to produce it. The industry's thirst for power is a critical challenge we must address. Beyond electricity, AI's massive data centers have a significant physical footprint on our planet. These are not small office buildings. They are colossal industrial structures that require vast amounts of land. A single data center campus can cover hundreds or even thousands of acres. This is land that can no longer be used for agriculture, housing, natural habitats. Companies often seek out flat, inexpensive land in rural or semi-rural areas, fundamentally transforming the landscape and the local community. The construction itself is a resource-intensive process, involving enormous quantities of concrete and steel. The digital cloud, it seems, is built on a very solid and sprawling foundation of concrete. Another critical and often overlooked resource is water. The thousands of servers packed into a data center generate an incredible amount of heat. To prevent them from overheating and shutting down, they must be constantly cooled. Many large data centers use water-based cooling systems, which are highly effective but also incredibly thirsty. A single data center can consume millions of gallons of water every day. This is often equivalent to the water consumption of a small city. This water is drawn from local sources, such as rivers, lakes, municipal water supplies, putting data centers in direct competition with residents and farmers for this essential resource. This demand for water becomes especially problematic in regions that are already experiencing water stress or drought. Many data centers have been built in arid locations like Arizona and Utah. However, in these desert environments, every gallon of water is precious. The sight of a data center consuming millions of gallons a day to cool its servers while local communities are asked to conserve water creates significant social tension and raises questions about our priorities. Is using a finite water supply to power AI a responsible use of a shared resource, especially as climate change makes droughts more frequent and severe? The physical materials required to build the servers themselves also represent a significant cost. Each server is a complex piece of hardware containing precious metals and rare earth elements. These materials are sourced through global supply chains that are often opaque and environmentally damaging. The mining of minerals like cobalt, lithium, copper can lead to deforestation, water pollution, human rights abuses in the countries where they are extracted. The life cycle of AI hardware, from the mine to the data center and eventually to electronic waste, is a global story with a long and often hidden chain of environmental and social impacts. AI's footprint is therefore not just local, it is a global network of extraction and production. The financial cost of building and operating the infrastructure for large-scale AI is astronomical. Constructing a single state-of-the-art data center can easily cost over $1 billion. This figure includes the price of the land, the building itself, and the tens of thousands of highly specialized servers and networking equipment inside. These are not ordinary computers. The chips required for AI training are GPUs. A single high-end GPU can cost tens of thousands of dollars. A large data center will contain thousands of these chips, pushing total hardware cost into the hundreds of millions. The price of building the physical homes for AI is staggering. This enormous upfront investment creates a significant barrier to entry. Only a handful of the world's wealthiest tech corporations have the capital required. Google, Microsoft, Amazon, Meta. Visual. A chart shows skyrocketing capital expenditures on data centers over the past 5 years. This concentration of resources means control is being consolidated in very few hands. Smaller companies, academic researchers, startups. The ongoing operational costs are just as daunting as construction. The largest expense is electricity. A massive data center can have a monthly electricity bill in the millions. Add the cost of water for cooling, salaries for staff, and constant hardware upgrades and replacements. This relentless drain means the AI business model is predicated on achieving massive scale. Companies must monetize AI services to recoup these investments. Ultimately, who pays for all of this? Companies pay with profits, but costs are passed on to others. Businesses that use AI services pay subscription fees. Consumers may pay with their data. That data is used to further train and refine models, creating a cycle of value extraction. As a society, we all pay indirect costs: strain on power grids, strain on water systems, and the environmental cost of increased carbon emissions. The billion-dollar bill for AI is not just a line item on a corporate ledger. It is a cost distributed across society. The immense resource demands of large-scale AI create a complex web of environmental and social trade-offs. The most direct environmental cost is the carbon footprint. Even with significant investments in renewable energy, the AI industry's explosive growth means its overall energy consumption is rising dramatically. This surge in demand can slow down the decarbonization of our energy grids, as utility companies may be forced to keep fossil fuel plants running to ensure a stable power supply. The promise of a clean, digital future is clouded by the reality of AI's reliance on carbon-intensive energy sources. The digital world is inextricably linked to the physical world's climate crisis, and AI is becoming a larger part of that equation. Beyond carbon emissions, the local environmental impacts can be severe. The constant noise from cooling fans in large data centers can be a source of noise pollution for nearby residents. The discharge of heated water from cooling systems can disrupt local aquatic ecosystems. The sheer physical presence of these massive, windowless buildings can alter the character of a community, transforming rural landscapes into industrial zones. These are often seen as NIMBY issues, but they point to a larger pattern where the benefits of AI are enjoyed globally, while the negative environmental consequences are concentrated in the specific communities that host the infrastructure. This creates significant social trade-offs. When a tech giant decides to build a data center in a small town, it often promises jobs and economic growth. While some jobs are created, many are highly specialized, and the actual number of long-term employees at a heavily automated data center can be surprisingly low. Meanwhile, the facility places a heavy burden on local public services. It consumes vast amounts of electricity and water that could have been used by residents or other businesses. This can lead to conflicts over resources and a feeling that the community is sacrificing its own well-being for the benefit of a distant corporation. The distribution of costs and benefits is often deeply unequal. The challenges posed by AI's resource consumption are significant, but they are not insurmountable. We have a range of practical solutions that can help us chart a more sustainable course. The first and most important pathway is a relentless focus on efficiency. This can happen at every level. At the hardware level, engineers are developing new, more energy-efficient chips specifically designed for AI computations. These chips can perform more operations per watt of energy consumed, directly reducing the power draw of data centers. At the software level, computer scientists are exploring new algorithms and model architectures that require less data and computational power to train, a field known as tiny AI, efficient AI. Another critical strategy is the transition to clean energy. Tech companies must accelerate their investments in renewable energy sources like solar power, wind power, to match their consumption. This means not just buying renewable energy credits, but directly funding the construction of new solar and wind farms to power their data centers. A commitment to 24/7 carbon-free energy would ensure that data centers are powered by clean sources around the clock. Data centers can be more flexible, shifting intensive tasks to times when renewables are abundant, such as midday for solar power. We must also rethink the physical design and location of data centers. Innovations in cooling technology, like liquid cooling using outside air and cooler climates, can dramatically reduce water consumption. Another promising idea is the reuse of waste heat. The vast amount of heat generated by servers is typically just vented into the atmosphere, but that heat can be captured and used to warm nearby homes, offices, greenhouses, turning a waste product into a valuable resource. This is already being trialed in some European cities, integrating data centers into the community. Finally, policy and regulation have a crucial role to play. Governments can create incentives like tax breaks, streamlined permitting. They can also require public reporting of energy consumption, water usage, carbon emissions. That data enables accountability and better policy. Technological innovation, corporate responsibility, and smart public policy can guide AI toward a powerful, accessible, and sustainable future. We are at a crossroads in the development of artificial intelligence. One path leads to unchecked expansion, an arms race to build ever larger models and more sprawling data centers, regardless of the environmental and social costs. This path treats planetary resources as limitless and prioritizes computational power above all else. It is a path of brute force, risking AI becoming a contributor to climate change and resource scarcity. If we continue down this road, AI's promise could be undone by its own unsustainable weight, and benefits concentrated in the hands of the few. The other path is smart, intentional growth. This path does not reject progress, but defines it differently. It prioritizes efficiency, circularity, and equity. Researchers focus on developing smaller, more capable models that can run on less power. Companies compete not just on the size of their models, but on their energy efficiency and their use of clean power. Policymakers create rules of the road that reward responsible innovation and ensure that the benefits and costs of AI are shared more equitably across society. This is a path of thoughtful design, not just raw power. Choosing this second path allows AI to continue to thrive. It ensures that the incredible potential of this technology can be realized without bankrupting our energy grids or depleting our natural resources. A sustainable AI is one that can be deployed more widely on smaller devices and in more communities around the world, rather than being locked away in billion-dollar fortresses. This approach democratizes access to AI, fostering a more diverse and resilient ecosystem of innovation. It ensures that AI's growth is aligned with long-term human and planetary well-being, rather than being in conflict with it. The goal is not to stop AI, but to steer it in a more intelligent direction. The choice between these two paths is not solely in the hands of a few giant corporations. It is a collective choice that involves researchers, engineers, policymakers, and the public. We must demand greater transparency about the true costs of AI. We must support research into more efficient and sustainable technologies. We must advocate for policies that put the long-term health of our communities and our planet first. The narrative that bigger is always better is a powerful one, but it is not the only story we can tell about the future of artificial intelligence. By making smart choices now, we can ensure that AI develops as a tool for broad-based progress, not as an engine of unsustainable consumption. As we have seen, the dazzling capabilities of modern artificial intelligence are built upon a very real and resource-intensive physical foundation. The story of AI is not just one of algorithms data, but also one of electricity, water, land, money. The current trajectory of building ever larger models supported by massive data centers presents us with critical trade-offs between technological advancement and environmental sustainability. The immense consumption of power, the strain on water supplies, the concentration of control in the hands of a few wealthy actors are not minor side effects. They are central challenges. However, this is not a story of doom. It is a call to action. We have the tools and the ideas to build a more sustainable and equitable AI. Through innovations in hardware efficiency, software efficiency, a committed shift to 100% clean energy, creative reuse of waste heat, and thoughtful public policy, we can change course. The goal is not to halt the progress of AI, but to guide it with wisdom and foresight. We can have powerful AI without a runaway power problem. The future of AI will be shaped by the choices we make today at this crucial crossroads. The power to build a better technological future is, and always has been, in our hands. Thank you so much for taking the time to watch and engage with this important topic. The conversation about the future of AI is one that needs to include all of us, and understanding the real-world costs of this technology is a critical first step. If you found this discussion valuable, please consider giving it a like to help it reach a wider audience. And if you want to continue exploring the complex intersections of technology, society, the environment, please be sure to subscribe to the channel. We have many more explorations planned, and your support makes it all possible. Thank you again for being here.